All right, thank you everyone for joining our webinar today. NEX10, Small, Robust, and PIM-Stable RF Interface for Mobile Networks. My name's Ben Stone, and I'm with RCR Wireless News. Happy to moderate today. Our speakers today will be Daniel Troxler, Product Line Manager, RF Connectors and Components at Huber and Suhner. Martin Wimmer, Director of Product Management for Rosenberger, and Ross Martinez, Marketing Manager for North America at Radiall RF Business Unit. Just as a quick note, the webinar and the slides will be available for download after the presentation this morning. Please be sure to enter any questions you have for our presenters during presentation as well, and we ask that you do your best to ask a specific, one of our specific presenters, if possible. So with that, I'd be pleased to give it away to Daniel.
Welcome to the NEX10 presentation. We are very happy you joined this webinar. My name is Daniel Troxler and I work with Huber and Suhner as product line manager for RF connectors and components. So let's look at the agenda. In this presentation, we will show you the challenges we saw for the next generation RF antenna connectors and how we solved them with our NEX10. We will explain the NEX10 interface and its features and benefits. Part of this presentation will also be the status and success of our market introduction. The main trends in the area of antenna connectivity that led to this development are 5G and MIMO technology, with an increase in data, but also an increase in number of ports per antenna. With more carriers, frequency band, and higher density on existing sites, PIM is a critical requirement for this type of connectors. Further reduction in size of modules and antennas, and at the same time more connectors, require solutions that fit the smaller radios and antennas and also save weight. The installation or mating of these connectors happens in the field. It is therefore key that the connector is robust and the interface design prevents against damages during mating. Based on these trends and demands, we developed the NEX10, a small, low PIM and robust connector. NEX10 is significantly smaller than existing connectors like 4310. We use the experience we gained with other connectors to design a PIM-stable solution. And we especially paid attention to the robustness of the interface with, on one hand, the long guidance for a mechanical robust connection, and on the other hand, design of contacts to ensure no damages can happen during handling and installation. The connector was developed in a cooperation of 3 leading connector manufacturers in this market: Radiall, Rosenberger, and Huber and Suhner. It is our goal to make NEX10 a market standard in the communication market. In a short introduction video, I'm going to explain the main aspects of NEX10 and its application before we then go into the details. With the cooperation of Radiall, Rosenberger, and Huber Suhner, we combined the know-how and experience of innovation leaders to create a new market standard. NEX10 focuses on small cell and in-building applications. Small equipment where space is of the essence. We offer 2 different coupling mechanisms that fit to the universal jack or female connector on the radio or antenna. One version is the screw version, and the other one the push-pull or quick lock version. Similar to the 4310 connector, the electrical contacts are separated from the mechanical mating mechanism, which provides stable PIM values independent of torque and under mechanical stress. The interface is easy to connect and designed such that no damages can occur while mating. NEX10 has a much smaller footprint than, for example, 4310. At the same space of 3 4310 connectors, can 5 NEX10 connectors be placed. The interface is IP68 protected, although we address customer requirements for additional weather protection boots. Boots are available for NEX10 connectors. We defined a sealing area on the female connector to standardize the boots. All in all, a thoroughly developed connector to be ready for today's and future application. On nex10.info, you can find more information about NEX10, including this video. In the video, we did see an example, a small cell application. NEX10 is the connector to be used in applications where PIM is required and at the same time, size is of the essence. For connections on antennas, radios, and filters. Based on the NEX10 interface, there are also multi-coax connectors available with 4 or 5 ports. NEX10 is suitable for indoor and outdoor applications. And with that, I hand over to Martin.
Thank you, Daniel, for the introduction. I'm Martin Wimmer. I'm Director Product Management for Cabinet and Site Solution Connectivity with Rosenberger, and I give you a more detailed overview about the interface specification. As already here by Daniel, we have 3 types, or 2 types. We have a universal jack and a screw and a push-pull type. The screw type will be, in my opinion, the standard for most applications, but in narrow spaces, in cabinet installations where you don't have enough space to apply a torque wrench, the push-pull is a choice. The NEX10 has a 5 mm outer contact element and a 1.5 mm center contact. The flange of NEX10 is with 12.7 mm by 17.5 mm. The footprint is 66% smaller compared to a 4310 connector, which allows a much higher density, already pointed out by Daniel. The thread is on the NEX10 M10 thread compared to M20 on the 4310 connector. A little bit on the lessons learned. When we started the development of NEX10, we all were part of the 4310 development and manufactured it, supplied it to the field. And very soon after 4310 approached the market, we were faced with the problem of the 4195 being tried to mate with the NEX10, and then the NEX10 contact sleeve gets damaged. We knew about, well, we found out about this problem, and we said, well, it's obvious there is a difference, that the connectors look different. It should be very easy to determine which connector should be used, but well, if you hang 40 feet off a tower, it's not always easy to see what connector it is. So we wanted to solve this problem and avoid that maybe a N connector or a T and C, which looks from the size maybe similar to a smaller version, is tried to be forced in, and then the connector on the antenna or the remote radio head is damaged. Also, when you hang 40 feet off the tower, it's not always easy to mate the connectors perfectly straight into the interface. And then again, it can very easily happen that the contact sleeve get damaged. Luckily, on a 4310, this interface is still big enough, so it's not so easy to damage the contact sleeves because they're still quite robust. But we realized if we make the interface so much smaller, go to less than half the size, also the contact elements get more and more fragile and even easier to get damaged when a wrong connector is tried to be pushed in, or if it's mated not perfectly straight. So I want to show you now how we did this. The first thing was, well, move the contact sleeve away from the expensive equipment. So in case they damage it, at least not the connector, the interface on the expensive antenna or remote radio head is damaged, then it's just a comparable cheap jumper cable which can easily be replaced, and you don't have to rip down the whole antenna or radio head. this was the first step for us to move it to the cable side, the contact sleeve. A nice side effect of this was also a reduction of size, because the thread now is much closer to the contact area. If I go back one slide, you see here we have on the contact sleeve and then the gap and then the thread. So with this step, it also allowed us to make the whole interface a little bit smaller, even if those 5 millimeters on the outer contact is same as other small PIM connectors in the field have. The overall appearance of the connector can be a little bit smaller. The next thing, how we wanted it to make it more stable, well, protect the contact sleeve from the inside and outside as good as possible. So on the inside, we picked dielectric extending inside the contact sleeve to give it more robustness, to avoid that some other parts can insert and possibly damage it. And the same principle we also applied then on the female side, where we have the slotted center contact element. So both fragile contact elements are protected with the additional dielectric surrounding it. Next measures that we took was the long guidance. So we ensure that when the contact elements actually get in contact, the connectors are perfectly aligned and they really meet in a straight way and in the right position. So the guiding of the connector was the next measurement. And last but not least, we fixed the coupling nut so it cannot fall back. So same principle as on an end connector. The coupling nut is always in the same place, and this gave us more protection. In case it's mated in an angle, it's pretty much impossible that the contact element can get in contact with the outer contact of the female side. And also, I mean, the guys in the field, they take off the protection caps, throw the jumpers around. This also protects the contact elements because they're further in the back and not so exposed. Another specialty of the NEX10 is the quick lock mechanism. On a quick lock, you always have the problem that it's not completely tight. You always have a little bit of relative movement of the male and female connector to each other. What this results in is that over the time during vibration, the little bit of movement creates little metal flakes, and the little metal flakes in the interface build up and they cause PIM at one point, because loose parts in the interface have this effect that they cause intermodulation. So we had a unique sealing situation that the O-ring actually acts kind of like a shock absorber. It's sealing radial to be sure, but also it has light axial component that puts some pressure, axial pressure between the two interfaces and minimizes the relative movement of the contact areas to each other. Also, the quick lock mechanisms that we chose for NEX10 is longer. We need more space, but due to the long coupling nut, to the protections that we have the space. And with this mechanism, it's a little bit smaller in the overall diameter and much more stable than the C-ring, which is known from a 4310 and relative connectors, that the connector can handle higher transversal cable pulling, and it doesn't open as easy as the C-ring. From the design features, most of it already mentioned by Daniel and shown before in the slide. Key to a low PIM connector, what everybody knows since 4310, the separation of the electrical and the mechanical contact area. This makes the interface independent of torque as soon as you made it and the radial contact is in place. It doesn't matter how strong you push the connectors together, the contact doesn't get any better and the PIM is there from the first contact it has. As shown in the slides before, robustness was our aim. We wanted to make it as robust as possible, and with the protective actions that we took, I think we did a very good job on it. The form factor, as small as possible, with moving the contact sleeve to the cable, the overall diameter got even smaller, even though the 5 millimeters contact sleeve with 10 millimeters thread, it's a very small form factor, and the flange with 66% smaller than 4 to 10 is quite a step too. This is a stability against vibration on the push-pull, as shown with the O-ring. Of course, the interface is IP68 without any additional weatherproofing, but in some harsh environments, in coastal areas where you may want to protect it, or in very cold areas where you have a lot of ice builds up, you maybe want to put additional weather protection boot around the interface to give it a little bit of extra protection. To allow the boot, we defined a special sealing area in the standard of NEX10 on the female, so that there is always the same diameter and length that allows the boot to seal to the female connector. Next, a little bit the electrical specification of the interface. The connector, it can handle up to 20 gigahertz, but really optimized best return loss values up to 10 gigahertz. You also see it in the return loss line. You get 20 dB to 20 gigahertz, but 30 dB at 10 gigahertz still. Interrelation, of course, 166 dBc at 2 times 20 or 2 times 40 watts, up to 6 gigahertz. The RF shielding, same as in the 4310. A screw version is always a little bit better than a push-pull version because the push-pull doesn't have the additional outer contact between the two outer contact elements from the male and the female. Therefore, the screw version has with minus 110 dB a little bit better shielding than the push-pull with 90 dB or 70 dB. Another issue we want to address, because I think this was our own fault in the beginning when we started promoting the interface, we always say NEX10 is optimized for quarter-inch cable. This does not mean it can't handle bigger cables. Of course, you can also go with the 3/8 or half-inch flexible or super flexible, can also be handled with the interface. Why we said optimized for quarter-inch, it's because of the diameter steps. If you look at the interface with 5 millimeters and then a quarter-inch cable connected to it, you have the minimal of diameter steps in the transmission line, and this allows the best return loss, the best electrical performance of the interface. But also in the qualification, we already proved against larger cables on the mechanical robustness of the interface to handle the bigger, the more stiffer cables. The highest we would see is a half-inch flexible or heliax or low loss. There are different names out for it. So the thick half-inch cable, the typical cables have a bending moment of 5 Newton meters, and also against this we already tested in the qualification. In the qualification, we performed a test. This was the first one, where we loaded a connector pair with 250 Newton at 20 millimeter distance, which, if you do the math, ends up at 5 Newton meters. And we loaded the connector pair for 60 seconds with this force. And there was no change, no effect to the connectors. They were still as stable, and no damage occurred during this test. But of course, we also know in the field, you don't want the connector to not be damaged. You also want good PIM performance. So of course, we also did a PIM test with the half-inch flexible cable. And of course, also according to the IEC 62037-2 with 2 times 20 watts, and we did the relative movement where we have special distance and the diameter where we have to move the cable around. And you see on the left 2 comparisons of the static measurement of the PIM, and also on the bottom the dynamic PIM result. As you can see, there was no big deviation, and the interface also guarantees the stable PIM performance in dynamic condition with the big cable. When we started the development, first we aimed for a little connector for small cell applications, but we also saw with the increasing ports on an antenna, when they go to 24, 36, or even higher on the ports count on antenna, installation time will increase dramatically. And also, I don't know, I don't want to connect 36 ports on antenna and this on 3 sectors. I think the risk of getting cables mixed up is very high, so the solution would be a multi-coax connector. What we have is a two different versions, one with 4 or one with 5 inserts. And with one mating, you have then 4 or 5 RF connections already. The size of the interface is exactly the same as the 7/16. We have the same flange size, and also on the cable connector, the coupling nut is also a 32 millimeter hex flats. So the guys can use the old torque wrenches that's still in the trucks. They can take it out and reuse it on the multi-coax connectors again. Since the interface, the single NEX10 interface, we proved already with the PIM stability and dynamic conditions on the push-pull and everything. So the multi-coax has the same outstanding PIM performance and return loss values. What we have in the single one, of course, also can be kept in the multi-coax connector. On the bottom right, you see the push-pull version, which we also made for the multi-coax interface. If you have 4 or 5 inserts, and one insert already has a mating force of 20-25 newtons. So if you have even more, 4 or 5 of those inserts in one connector, you very easily get over 100 newton mating force if you try to mate it. And that's why we decided to make a special quick lock mechanism where it's actually a 2-step connection. First, you plug the connector in and you make the connection, and in a second step, you lock it. We wanted to separate the mating force and the force from the quick lock mechanism. We want to separate it because this would have increased the mating force additionally. The next slide, you see the form factors again, a drawing on it, and you can see we really have the same size as the 7/16 with 32 by 32 millimeter flange and the 32 millimeter hex flats on the coupling nut. And the 4 and the 5 port connectors are also the same outer appearance. The pin in the middle guarantees the right orientation of the interface, and due to the design of the interface, it's also not possible and no damage will occur if someone tries to put a 4-port interface into the 5 one or vice versa. Okay, so this was my summary from the technical part. I hope we get a lot of more questions after on it, and I will hand over to Ross now to give an update on the general project.
Thank you, Martin. Hello, everyone. My name is Ross Martinez, and I'm with Radiall. I'm the marketing manager for the RF for North America. Thank you for your participation today, and we really appreciate that you guys have taken the time out to hear about this exciting and innovative product, NEX10. I'd like to provide you just a quick status and timeline and define the commercial strategy behind the NEX10 development. In order to do that, kind of give you just a quick background, into what drove the development. Our respective companies saw that with the deployment of 5G and densification of the network, as well as the growth of small cells, there was inherently going to be a need for a small, robust, and low PIM connector. So, capitalizing on our collective design experience and market expertise and our positions in the telecommunications space, Radiall, Suhner, Rosenberger, we all worked together to create the consortium that co-developed NEX10. NEX10 was officially launched in 2017. Today, we are all actively producing the full standard product portfolio in production volumes, including connectors, adapters, cables, as well as some microwave components. NEX10 is a proven product. It is gaining a tremendous amount of traction within service providers, OEMs, filter, and antenna manufacturers. Since the launch, we have collectively implemented over 350,000 discrete connections. I want to be clear about that it's not with the multi-coax yet. Those are all discrete connections, as well as multiple design wins that are not reflected in the numbers today, which, considering that 5G hasn't really officially rolled out in huge volumes yet, that's pretty substantial numbers, we think. So a good gauge to get a feel for the NEX10 is if you walk in any telecom trade show today and you see a small interface, a low PIM connector on there, it's more than likely going to be a NEX10. So it is a proven connector that is designed in today. Speaking of trade shows, we are excited to announce that we will be showcasing the multi-coax version of the NEX10 next week at Electronica in Munich, with production coming in Q1 of 2019. Go ahead and move on. So on to the commercial strategy. So the NEX10, as I mentioned, was established as a collaborative effort with the goal of creating an industry standard for small, robust, and low PIM connections. We felt it also important to expand NEX10 via strategic partnerships / licensees to capitalize on other strengths from other customers or companies, as well as to expand the NEX10 brand in the marketplace. We do have some key developments / licensees in the works, and we'll be happily announcing those as soon as possible, as soon as they can be made public. As of today, I can't really go into too many details, but we should see something here coming up shortly. Also, as part of the long-term strategy, the consortium has decided to move forward with the IEC standardization, and we will be launching that next year. Go ahead and move on. So in summary, as my colleagues defined today, with the emergence of 5G, there will be needs for increased data, the increased number of ports, low PIM connections that are small size and low weight, that are robust and foolproof, you know, where you limit the exposure to damage of the equipment. NEX10 is that solution to address those challenges today. NEX10 provides a compact, low PIM interface. It enables more connections in much smaller areas, as well as the multi-coax. You know, you get 4 to 5 connections in the space of a 7/16 connector. And as Martin alluded to, you can still use your existing tooling, your torque wrenching. So that's a pretty awesome feature. As far as the robustness and ease of installation, well, NEX10 scoop has a scoop-proof interface. So it prevents damage during the installation process, you know, which ensures some level of security and reduces the fear and cost of damaging connectors during installation, which ultimately leads to lost revenues, site downtime, and customers not getting supported. So obviously that's an important feature. So I believe we are the only ones that actually have that on this interface compared to what's out in the market today. Another key aspect of working with the consortium and licensees is that customers have multiple sources with the NEX10 licensees, and we guarantee the interface compliance, the quality, intermatability among those suppliers. So when you buy a NEX10 product from any of the suppliers today, you are guaranteed to have a compliant product and a quality product. And as I mentioned, for long term, we will be initiating the IEC standard this next year. In closing, I do want to reiterate that NEX10 is a market-proven solution, and it's available today. It's not vaporware. It's not marketing material. It's an actual product that is in production, and the suppliers today can support volumes today. And it is from leading manufacturers. It is an ideal solution for small cell antennas, DAS, in marketing and building architectures and MIMO applications. And we are here to support your NEX10 needs. So if you have questions, we'll open that up here shortly. Before we do, I do want to reiterate or want to make you aware that we do have a nice resource. It's nex10.info, the website. This is a consolidated place for information regarding NEX10. A lot of the features we talk about today are there. The video is there. It's a great resource, and as well as a central repository for updates. What I would like to also mention is at the bottom of the thing, if you have a specific question that you want to ask one of the suppliers on, or contact the suppliers on the site, you would go down to the bottom of the page, and the link here where it says contact, you can contact Wimmer, Radiall, or Rosenberger directly, and as well as you have our contact information. And that's really mainly all I have. Thank you for your time, and we'll open now up to questions.
Great. Yeah, thanks everyone so much for wonderful presentations. So I'll just start it out here with sort of ask maybe the three of you, but let's start with Daniel, Martin, and then go to Ross, so in that order. But what is the market penetration today, and are your suppliers ready to provide high quantities of this?
Right, so NEX10 is already used by OEMs, by manufacturer of communication equipment, filter manufacturers and antenna manufacturers, and also companies that provide jumpers with NEX10 are out there. So this requires also approvals of obviously operators to do so. As outlined by Ross, we are ready to produce high volumes. We are producing high volumes already. Besides, we were talking about market penetration, or the question was about market penetration. We will add suppliers to NEX10. We will open up the customer base of the three we are at the moment. And as you can see also on nex10.info, JMA is another one also providing NEX10 connectors. And there are more to come.
Great. Does anyone else, any other panelists have any thoughts on that? Okay. What is the main differentiation to other interfaces in the market?
Does this go to me as well, or Martin? But maybe I can give you an answer on that one as well. So when we look at the current interfaces in the market, I think the key differentiation of NEX10, and I think that's one of the aspects going into the future, is the size. I think we are the ones with the 12.7 to 17.5 millimeter flange. It's a small connector. It's PIM stable and it's robust. So on one hand, you can compare specifications like PIM, like return loss, or like flange size. Especially on flange size, we make a difference, or on size, let's say thread size compared to other interfaces. On the other hand, there are significant advantages or differentiation to other connectors in the market in terms of robustness and handling. Like Martin outlined in detail, that the interface design is such that no damages can occur while mating, and also during handling of these connectors, which brings also a significant advantage to have good quality connections in the field. So in summary, size and robustness.
Great. Do any of our other speakers have any thoughts?
Yes, I would like to add something. When we started developing, it was end 2015. We started with development of NEX10, and each of us brought a first draft to the table when we met together. And we have to admit, two of us had a same concept as the 225, which was mentioned in the question. Here, it was a scaled down force return. We said, well, nothing easier. You have a force return, you know this works, so make it smaller, and you have your solution for the future for the small cell application. But in the first meeting, when we brought those together, we saw that it does not work. The robustness features, the features with 4195 being mated into a force return, the size we picked was 5 millimeters. We have the same problem with the end connector. If you try to put an end connector in our original design, which was basically we also had a 5 millimeter outer contact and no air dielectric, so basically it was a 225 what we brought to the table. You damage the contact sleeve. It does not work. We saw this was critical, and that's why we changed our design and needed a little bit longer. We started 2015, and the first launch really was 2017. Or it was electronic 2016, so about 1 year until we first launched it. We did the pre-qualification, and then in 2017, the first OEM brought out the radio, and since this, I think many of you already handled NEX10 in the field. And really, the robustness. This is a differentiation, and that's why we changed our design, which was in the beginning very similar to a 2 to 5 from nowadays.
Thanks. What is the torque spec for the hex version of the NEX10?
It's 1.5 Newton meters. The proof torque, we can go up to 10 Newton meters without any damage. Recommended torque was 1.5, but we know installers, they usually don't carry torque wrenches. We're aware of that. So Force 310 has 5 Newton meters. So even if they do a 5 Newton meter, which it's calibrated in their arm, it's also okay. But standard-wise, 1.5 would be the specification.
Wonderful. And with the emergence of the new 2.25 connector that supports half-inch cable and requiring no licensing, how relevant is the NEX10 for the future?
Well, the licensing is, well, 2 to 5 basically also is a licensing issue because it also falls under the same pattern as the Force 310. I mean, everybody that has a Force 310 license will also be possible to do a 2 to 5. But like Ross showed, we will also do IEC standardization, and we are already in the process of licensing until IEC is out, because IEC will take a time. We need some time to prepare it, to get all the documentation, to hand it in. We are doing that right now, and in the next IEC meeting, which is I think April, May in 2019, the IEC filing process for NEX10 will also start, and then it's a standard interface by IEC, and there won't be a problem either anymore. What it says how relevant will NEX10 be compared to 2 to 5. For me, is how relevant will 2 to 5 be compared to NEX10, because right now NEX10 is the interface which is already in the market. We see in North America, we see, like Daniel said, it's already approved by OEMs, by operators, and OEMs already has radios out, more and more radios. If you look at trade shows, you see equipment from OEMs also with NEX10 on it. Jumpers are available. You can also search different major jumper suppliers, and you will see a NEX10 in their portfolio. We have combiners, antennas are also the first ones available. I think right now, if you say relevance, right now, NEX10 is, from my understanding, what I see in the market, more visible than a 2 to 5 right now.
If I may add to your points, to your very well mentioned points, Martin, I think to the future aspect of this question, future, we see a clear trend to the size. Size is a critical factor in the future. And this exactly is the main point we also address with NEX10. So that was to us a key point when we developed NEX10. We really focused on to make a very compact connector, to have a connector for future applications where size matters and where size is very critical on radios and antennas. So looking into the future, I think NEX10 addresses exactly these very critical aspects.
Wonderful. So somewhat longer two-part question from an audience member. They say, as an application engineer for this market, they encounter customer misunderstanding about the difference between IP67 and IP68. He sees that NEX10 is rated to IP68. Can you explain what that means exactly? And then in terms of network equipment applications, does that mean that NEX10 is appropriate for applications where flooding can occur?
Yes, I apologize. That was an error of my missed presentation part. Of course, IP68's question is absolutely right. IP68 should always have the addition, what kind of rating, because it's not defined in the standard. IP68, what we tested NEX10 for, was for 1 meter water, underneath of water, for 24 hours. So to the difference of IP67 to IP68, and I hope I get it right now, IP67 is between 0.1 and 1 meter for 1 hour, and IP68 can be anything that is higher than IP67, but it's not defined exactly what. So you see very often the 25 meter for 1 hour. That's a very common one, and I think 4310 was specified like this, that it's for 25 meters underwater for 1 hour what it can withstand. As the questioner asked about flooding, I think it's very unlikely that you have 25 meter of flooding and only for 1 hour. That's why we specified the NEX10 and designed it for 1 meter for 24 hours, which should be closer to a flooding situation than 25 meters for 1 hour.
Great. Daniel or Ross, do you guys have any additional thoughts?
That was a very valuable question, because this is a topic we often see with customers. To be very specific on this one, just to add to that, it's always a mated pair, you know, because they're waterproof specifications in different conditions, but what we specify here is a mated pair of NEX10.
Great. So how is the multi-NEX10 connector keyed?
Let me switch to this slide. Here you can see it. We have the keying. So different variations of keying. I mean, if you know it for, I think most of the listeners may be familiar with the power connectors, which is very famous with the radio heads in North America from various operators, OEMs. They have the keys on the outside and the slots where they dive in. This is from the machining perspective quite difficult if you don't go into die casting, and then for volume for ramp up you thought about also about machining those parts. So we picked a coating which is just one hole which is off-centered. So you see on the female side you see a pin in the middle that is off-centered, and on the male side you see the hole. And this guarantees that only in one position it fits in. Also very nice when you try to make it, it slides very nicely, very easily, because you're already with the body of the male side, you're already inside the circular area. So you have a guiding that you're aligned, and then you just twist it until the pin reaches the one hole and it slides in nicely. And this is the same for 4 and 5, but like I said, the interface itself, because the contact area is very far in the back, and the contact elements here are also in the back behind this surface area, then the interfaces in the front guarantees that a 4-1 and a 5-1, if they get mixed up, don't cause any damage to the interfaces. Was this understandable enough?
Yeah, thank you. So how will you address the 5G market at 28 gigahertz and 39 gigahertz and above? Will there be subsequent higher frequency versions to address 5G?
Well, then I start again. I don't think that for those frequencies you still have a separate antenna and a radio head. What I see more in this is the active antenna systems, where you have the antenna integrated into the small cell or into the equipment already, and it's an active antenna system where you just connect with fiber and power. We think for those applications you won't have a jumper solution anymore.
Right.
And this also aligns what we see and hear with the OEMs that we work with.
And what tools will be needed to connect and install NEX10 in the field?
Well, if it's a push-pull, then no tool will be required at all. You can just plug it in. And with the screw version, we have a 11 millimeters hex flats. Don't ask me the inch size yet on it.
And as Martin mentioned, with the multi-coax, you have the same tooling you use for 7/16, so same torque wrench. So
awesome, thanks guys. Which major vendors, antenna, base station, equipment vendor, have or are using the NEX10 connector?
Sorry, go back to the other thing, it's actually a 7/16, I think, should be the thing for the US colleagues. So a 7/16 Allen key should be suitable for the NEX10 coupling nut.
Awesome. And to ask the question again, a different question, which major vendors have or are using the NEX10 connector?
That's a tricky one. I think, like I said, as we mentioned before, if you walk any trade show today, you'll see NEX10 on there. So with all of the big OEMs, for sure, quite a few antenna manufacturers as well. So.
Okay.
As Ross stated in the thing, we are already in licensing process right now with various connector manufacturers. The first one, if you look at NEX10.info, you will see already the first manufacturer which got a license for NEX10. And step by step, when we finish the various contracts that we're working on right now, we will add those companies to NEX10.info. Please understand that due to NDAs that we also have with the people in place, that we cannot announce this right now.
Mm-hmm.
Correct.
Yeah. What is the, perhaps related, but what is the adoption now or future plans for NEX10 with the top OEMs?
Well, we are working with OEMs on it, and you also see from one of them already the small cell audit with NEX10 for, I think, middle of 2017. They started launching it, and according to the jumpers and connectors that we sold, there are already plenty of them installed in the American region already. What I want to also say, the development with NEX10, we never aim to replace a 4310. A 4310 will still be the standard interface for macro side, for radio heads for the macro sites, where space is not so critical. With NEX10, we are aiming more for small cell applications, kind of like this little brother of 4310, same as it was in the past with the 7/16 and the N, and there will also be a coexistence of 4310 and NEX10. And also in this field, we are working with the major OEMs.
Awesome. Will it also be a hand tight type connector, a part of the push and pull and nut torque ones?
Theoretically, that would be possible, but we didn't go into that because we simply didn't see the market. Because on 4310 we have the 3 options, but basically only 2 are used: the quick lock and the screw version. So that was the reason why we didn't go into that with NEX10. I don't know, Martin, Ross, anything to add?
Agreed. That's the same scenario we've seen as well.
When we start with 4310, we put of each connector, plenty of connectors on stock to be prepared for the ramp up. And I think we still have the same amount of hand screw on stock what we produced initially. So if anybody wants hand screw, you can order it by us, but we don't.
Make great. Fishing lures, fishing weights, great.
Is the connector field installable, or are these factory installed?
Of course, there will also be field installable connectors available. Yeah.
Okay. And is there a limitation? Go ahead.
Maybe if I can add to that, this is not so much basically a limitation or a topic of the interface. It's more of the cable entry. So, but these type of connectors, field installable connectors to whatever cable, they can be designed and produced.
And have the testing standards been established for each of the carriers?
I do not completely understand this question, to be.
Okay, no worries. Which testing equipment do you recommend for this technology?
So maybe to these 2 questions, I don't know exactly how to understand these 2, but maybe we can elaborate a little bit on what we did. So we tested a NEX10 as we test other interfaces as well inside the consortium according to the specification we have out there. To the second question, I think this interface can be tested the same way as other interfaces, and we provide also test adapters with NEX10. Test adapters specifically designed for return loss and insertion loss or other electrical measurements, for example, but also 24310 or especially 716 for PIM measurements.
Awesome, thank you. And is there a limitation of NEX10 with FDD or TDD use?
I think NEX10, there is no limitation. NEX10 is designed for PIM application, so definitely for FDD, but it also can be used for TDD application, especially as I mentioned in the beginning, where you have different technologies at the same site. As this is sometimes used, then PIM is very critical. And of course, NEX10 can then be used for both technologies.
And what is the price delta compared to larger low PIM connectors like 4.310?
I think that's a case-by-case scenario. Obviously, volumes are going to drive it. Not an easy one to address.
Okay. So the initial guidance was that NEX10 was optimized for 3/8 inches cable, although it could in fact support half-inch coax. It was not recommended. From this presentation, it seems that the half-inch support's being highlighted. Could you elaborate on the half-inch coax support?
Optimization cable is a 1/4 inch, not 3/8.
Yeah, initially we said it's a 1/4 inch because the 1/4 inch fits from the diameters, from the outer contact. You have the 5mm outer contact, and then it's a very nice, very smooth transition from the diameters to a 1/4 inch cable. That's why we said at the beginning, always optimized for 1/4 inch. The 1/2 inch, that's why we also took it up, because we got those questions a lot in the past. It's no problem to make a bigger cable on the connectors. There were also end connectors for 7/8 inch and larger cables. It doesn't look pretty. It's not ideal from the diameter steps, and the critical part on a big cable on a small connector, it's always the mechanical robustness. So what we see, if the cable is very stiff, then of course each cable movement moves the bending moment, which is on a 1/2 inch, usually around 5 Newton meters. This moment will be transmitted to the female connector, to the panel connector, and to the interface. So we have to ensure that the interface is robust enough to handle the 5 Newton meters of torque on it. And we verified this also in the qualification. There's no problems, there's no damage occurs to the interface. And also in the PIM test, we showed that also the PIM values is no problem. A bigger issue on the big torque from a cable to the connector, the weak point is not the interface. The weaker point here is more the connection where you screw it on. If you have, of course, a 1/2 inch flange, what we have here is 12.7 by 17.5 millimeters. You get a very high leverage onto the screws that connect to your equipment. So the weaker point here is more the screws that connect the flange maybe to your aluminum chassis in your radio head or to your antenna bottom. But the interface itself is not the problem. And in order to solve this problem, if there is really or would be a problem, it's very easy to make the flange bigger. You can always make it bigger, but you cannot make a big flange what we have on a 4310 or a 225. You cannot make this one smaller. So what we want to show on applications where you don't have the huge moments on, we can go down to a 12.7 by 17.5 millimeter flange. Bigger is always possible if the mechanical robustness is needed for it, because the weak point in the test is not the interface or the connection of the interface, it's the flange and how the flange is connected to the equipment.
Great.
But the qualification also showed that the standard flange with 12 millimeters, and this is this picture, you can see the standard flange with 12 millimeter by 17.5 millimeters. So we also loaded it so that the highest leverage goes to the short side, and then even the small screws had no problems, there was no damage to it, and the flange, there was no damage to it. So the standard interface, the standard flange size can handle the 5 Newton meter bending moment from the half-inch cable.
Great, thanks. And I know we do have a lot of questions from the audience, so I'd like to just let everyone know that we do only have time for a few more questions, but we will be happy to follow up with you, and these questions will be shared with all of our panelists. Sorry, lost my place. Can you please address field connectorization of NEX10 jumpers, i.e. challenges, testing, and recommendations?
Yeah, then I take it again. In general, there's no specification, like Daniel said, to the NEX10. A field connectorization does not depend on the interface. The critical part on a field connector is always the connection from the cable to the different connector parts. And there it doesn't matter what kind of interface is on the other side. So for field insulation, it's always important to work clean, so that you don't have metal flakes, that you don't have additional dielectric remaining in the contact area of the outer contact, so you don't scratch the center contact when you remove the dielectric. It's more the basic cable preparation, but there is nothing special to a NEX10, which is different to a 4-10, 7/16, or any other interface being used in the market right now.
I would just encourage that to follow the installation data sheets, the installation instructions on the data sheets, accurately as possible.
Wonderful. And is there a limitation of the using of NEX10 regarding the frequencies? Will high bands for 5G and low band frequencies for 4G be supported as well?
I think it's a good question that you picked up here, because I think it's very important that we can emphasize here that NEX10 works from low frequencies up to 20 gigahertz, optimized up to 10 gigahertz. So it will work in the mentioned bands without any problems.
Okay. And what kind of cable sizes are planned to be suitable for multi-coax version?
On the multi-coax, we really have a limit to the cable size. On the single NEX10, like we pointed out, no problem, you can go up to a half-inch. On a multi-coax, due to the size that we picked, you cannot go bigger than a 1/4 inch. Smaller cables are also possible, but due to the distance to the pitch of the single interfaces in the connector body, any other cable would draw the connector bigger and bigger, and it wouldn't be possible to have the connector this footprint. So the limitation for multi-coax really is 1/4 inch cable, but not for the single interface. On the single interface, 1/2 inch flexible or low loss or Heliax, how it's called in the market, the different regions, no problem.
Wonderful. And I think we have time for one last question. And again, I want to just thank everyone so much for a really awesome session here. A lot of great questions. We will do our best to follow up as well. So final question, are these multi-coax solutions already available at all 3 suppliers, or is that only Rosenberger?
Yes, I mean, this is the consortium development, so the multi-coax is from all 3 suppliers.
Great. And do you guys have any maybe just final thoughts, the 3 of you, for our audience?
Maybe I would like to sum it up with the decision, if it's made right now, what interface to choose. I think for future applications, I think with 4310 we learned it's a great interface. We were part of the development, and I still think it's a great interface, but we saw there are weak points which can be improved. And I think plenty of guys in the US that are listening to us know about this problem, and they experienced it maybe in the field if they had 4195 in the system before. There is a problem, you can damage the connector. We took measures. We also have connector solutions for 4310 available to protect the contact sleeves. But why, if you start with the new connector interface, why settle for an interface that has the same weak points as 4310? I mean, the interface is even smaller than a 4310. The contact elements are even more fragile. That's why we took the measures to make NEX10 as robust as possible and make sure that the guys in the field cannot damage it. When we developed 4310, we have to admit we were not so close. We didn't get the feedback. We were just looking, ensure that there can't be any installation errors, that as soon as they made it, you get a good PIM and you get good water protection, and it's not depending of torque. This was good. This was back then. That was what we were aiming for. But we neglected kind of the problems in the field that can occur. I have to admit, I've never been outside on a tower installing it, but with the problems that we heard with 4310 in the beginning when we launched, we learned to understand those people and how it works in the field, and that's what we really tried to consider with the development of NEX10, to make it as robust as possible, to really ensure that, if, like I said, if you hang 40 feet up the ground and you see a small connect interface, I understand that you don't see right away, that's a NEX10 and not an N or a TNC or whatsoever, and you maybe try to put the red cable or whatever cable with N's or TNCs that you have, you try to put it in, and then the connector on the radio is damaged. Well, then explain your boss, well, I tried to put the wrong cable in and it damaged the radio head, we need a new radio head. That sucks.
Yeah.
Yeah. That's a
I think customers have to do a risk evaluation on this and determine, the connector, which is a small portion of the overall cost. Is it worth setting a site down for a damaged connector because someone scooped in the contact and damaged it? So I think that's the one value that we have over all the competition out there for NEX10 is that have that scoop-proof design that eliminates. I mean, obviously, if there's enough, somebody can damage a contact, but for the most part, the design feature in the NEX10 protects the inner contact. So, something to consider from a customer perspective. Is it worth risking over a connector cost to have a site go down based on saving $1 or $2, or even just picking one supplier or one connector over another? I think NEX10 is approved, like I said, is a proven product in the marketplace, and there's reasons why a majority of the OEMs are using it today.
So if you today have to decide what you're going to use in the future with the requirements on robustness and the size, with the modules becoming smaller, I think NEX10 is definitely one of the best solutions.
Okay, great. Well, thanks everyone so much. I think this was a great presentation today, and thanks to our audience as well. Everyone, have a great rest of your day, and that concludes our webinar for today.